By every known law of physics, our galaxy should be tearing itself apart right now. The stars at the edge of the Milky Way are moving too fast for gravity, as we understand it, to hold them in place. The outward motion is too strong. The visible mass is too low. The structure should fail. The framework should collapse. Yet the universe holds. For 80 years, we have hunted dark matter as if it were merely a missing particle, something to trap, isolate, and name. But that may be the wrong perspective. This is not a story about a hidden ingredient. It is a forensic investigation into the invisible scaffold that prevents reality from crumbling. So how do you map a blueprint that you cannot see, touch, or directly interact with? The invisible scaffold reveals itself in only one way. It passes straight through you. Don't panic, but you are currently under bombardment. Right now in this room, an invisible torrent is washing over you. Every single second, according to current models, roughly 100 trillion dark matter particles stream through your fingertips, pierce the Earth's crust, traverse the molten core, and exit the other side without slowing down. To these particles, the solid rock of our planet is as empty as a vacuum. They are WIMPs, weakly interacting massive particles. They are relics of the Big Bang, unable to interact through the language of electromagnetism. They do not reflect light, they do not carry charge, and they do not collide with atoms. They pass through you as if you weren't even there. For most of scientific history, we assumed that we were the substance of the universe. We believed that the stars, the gas, and the atoms that make up your blood were the main event. We were wrong. We mistook what was visible for what was fundamental. Visible matter, everything in the periodic table, is just the decorative cladding. We are the bioluminescent foam floating on top of a deep, dark ocean that outweighs us 5 to 1. This invisible ocean is not just stuff filling the void. It is the structural integrity of the cosmos. Without it, the large-scale structures that gave rise to the sun would not have formed, and the Milky Way as we know it would not exist. We are not the builders of this universe. We are just the guests living inside its walls. And to understand the architecture of our home, we must look for the cracks where the visible laws of physics begin to fail. Imagine a NASCAR race where the cars enter the turn at 200 miles per hour. Friction and banking keep them on the track. But now imagine they speed up to 2,000 miles per hour. Physics dictates that the tires should lose their grip and the cars should be flung outward. In the 1970s, astronomer Vera Rubin looked at the cars of our cosmic neighborhood, the stars on the outskirts of spiral galaxies like Andromeda, and found them breaking the speed limit. Rubin was conducting what amounted to a massive energy audit of the cosmos. According to Newton's laws of gravity, which govern our solar system, speed should drop as you move further from the center of mass. Mercury whips around the sun. Neptune crawls. We expected galaxies to follow the same logic, a bright, heavy center surrounded by a fading disk, where outer stars drift lazily. But the audit revealed a massive discrepancy. Rubin found that the stars at the outer edges of spiral galaxies were moving just as fast, sometimes faster, than those near the dense core. At these velocities, roughly 250 kilometers per second, the centrifugal force generated by the rotation should have overwhelmed the gravitational pull of the visible matter. The galaxy was spinning so fast it was trying to tear itself apart. By all rights, these stars should have been ejected into the intergalactic void billions of years ago. The fact that they remained locked in orbit implied a terrifying structural reality. The visible galaxy, the stars, the gas, the dust, was not the whole structure. It was merely the illuminated hub of a much larger invisible machine. Rubin's data suggested that every galaxy is embedded inside a colossal sphere of unseen mass, a dark matter halo. This halo acts as a gravitational framework, providing the additional mass needed to keep the high-speed stars bound to the galaxy. We had found the scaffold. But as we tried to map it, we discovered that the interaction between the invisible frame and the visible facade was far more volatile than we imagined. Once we accepted the existence of the halo, we tried to simulate it. We fed the laws of cold dark matter, commonly abbreviated as CDM, into supercomputers to see how these halos would form over billions of years. The simulations built a sturdy universe, but they predicted a specific flaw in the architecture. Computer models insisted that dark matter should pile up in the center of galaxies, creating a sharp, high-density spike known as a cusp. But when we observed real galaxies, especially smaller dwarf galaxies, we saw a flat, low-density core. The structural density didn't match the blueprint. This became known as the cusp core problem, and for a while it threatened to debunk the entire theory. The mistake, it turned out, was assuming that the cladding, the ordinary matter, was passive. We had treated stars and gas as weightless paint on a steel frame. In reality, the paint is explosive. New high-resolution simulations such as the FIRE project, short for feedback, in realistic environments revealed the violent mechanics of baryonic feedback. When a galaxy forms, it is a chaotic engine. Massive stars ignite and quickly die in supernova explosions. These aren't just fireworks, they are pressure waves of immense power. When thousands of supernovae go off in a concentrated area, they act like a thruster, blasting vast amounts of gas out of the galactic center. This sudden evacuation of mass changes the local gravitational field. With less gravity holding it together, the dark matter in the center relaxes and expands outward. The sharp cusp is smoothed out into a flat core. The visible matter, through sheer explosive force, pushes back against the invisible frame, reshaping the very skeleton it rests upon. This proved that the relationship between dark and light matter is a dynamic equilibrium, a gravitational tug-of-war. But this solution relies on the assumption that the two are physically distinct components interacting through gravity. To prove that, beyond a doubt, we needed to find a place where the two had been forcibly ripped apart. If gravity alone can't hold galaxies together, then either our physics is incomplete or something invisible is doing the heavy lifting. But if we could find a system where the structural frame had been separated from its visible components, we would have decisive evidence. What happens when two collisionless objects pass through each other at high speed? Almost nothing. They pass right through. But if they carry matter that interacts electromagnetically, that material can collide, slow down, and be left behind. For decades, skeptics argued that the dark matter halo was a mathematical fiction, a fudge factor invented to patch up our ignorance of gravity. Perhaps there was no invisible matter. Perhaps we just needed to tweak Newton's equations, an idea known as modified Newtonian dynamics, abbreviated as MUND. To distinguish between a hidden substance and a modified law, we needed a laboratory experiment on a galactic scale. We needed to smash two galaxy clusters together and see if the gravity could be separated from the gas. Nature provided that laboratory 3.7 billion light-years away, in a system known as the Bullet Cluster, formerly cataloged as 1E0657-56. The Bullet Cluster is the aftermath of a high-speed cosmic accident, where a smaller subcluster plowed through a larger one. This wasn't a fender bender, it was a collision of titans. To analyze the wreckage, forensic astronomers used two different lenses to map the debris field. First, they used X-ray telescopes like NASA's Chandra to map the visible matter. In galaxy clusters, the vast majority of normal baryonic mass isn't in the stars, but in the hot, diffuse gas between them. As the two clusters collided, this gas slammed together. Electromagnetic forces created immense friction, heating the gas to millions of degrees and slowing it down. The intergalactic gas collided and stalled near the center of impact, like the crumpled hoods of two cars in a head-on collision. Then they mapped the gravity. Using the Hubble Space Telescope, astronomers looked for gravitational lensing, the way the cluster's mass warped the light from background galaxies behind it. This technique maps mass directly, regardless of whether it shines or not. The result was shocking. The gravitational map did not line up with the gas map. The X-ray gas, the majority of the visible mass, was stalled in the center, but the centers of gravity were located far to the left and right, moving outward with the galaxies. The mass had passed straight through the collision, as if the friction didn't exist. This was a structural separation event, what engineers might call a chassis separation. The visible cladding, the gas, had been stripped off by the impact, but the invisible frame dark matter had effectively passed straight through the crash, carrying the gravitational center with it. This proved that dark matter interacts gravitationally, but it does not feel the electromagnetic friction that stops normal matter. It is a substance distinct and separable from the atoms that make up our world. If the Bullet Cluster proved that the frame can exist without the cladding, then the universe should technically allow for the reverse, a building made entirely of cladding with no frame at all. For a long time, this was purely theoretical. Every galaxy we studied seemed to be embedded in a dark matter halo. But in 2018, the Dragonfly telephoto array spotted an anomaly that broke the pattern NGC 1052 DF2. DF2 is an ultra-diffuse galaxy. It is as wide as the Milky Way, but contains only 1/200th of the stars, making it appear as a faint, diffuse smudge against the blackness of space. It is a naked building, a structure composed of walls and windows, but apparently missing its steel beams. When astronomers measured the movement of the globular star clusters within DF2, they found something unnerving. In a normal galaxy, these clusters should be buzzing around at high speeds, agitated by the gravity of the invisible halo. In DF2, they were moving sluggishly with a velocity dispersion of only about 7 kilometers per second. When you plug these numbers into the equation, the result was a ratio of 1:1. The total mass of the galaxy was effectively equal to the mass of its visible stars. There was no room for dark matter. The halo was missing. This discovery triggered a fierce debate that continues to this day. Some researchers argue that DF2 is actually closer to Earth than we think, which would skew the math and make it a normal, albeit dim, galaxy. Others suggest the dark matter was stripped away by a larger neighbor in a process called tidal stripping. But philosophically, the naked galaxy poses a lethal threat to alternative gravity theories like MOND. If dark matter is just an illusion caused by a modified law of gravity, then that law must apply everywhere equally. You cannot turn off a law of physics just because you are in a different neighborhood. Gravity should be modified in DF2 just as it is in the Milky Way. The fact that DF2 behaves according to standard Newtonian physics without the need for dark matter suggests that dark matter is not a rule, but a component. Just as you can find a car engine without a chassis or a chassis without an engine, you can find galaxies with different ratios of dark to light matter. We have isolated the frame. We have watched it crash, and we have found places where it is missing. We know it is real. We know it is heavy. We know it is the scaffold upon which we stand. A universe where gravity changes its rules everywhere should not allow exceptions. And yet, here is one: a galaxy without a structural frame. This confirms that the frame exists, but it leaves us with a haunting realization. If this massive structure is real and if it is everywhere, why, when we build the most sensitive ears in human history to listen for it, do we hear absolutely nothing? The quietest place in the universe is buried 1.5 kilometers under an Italian mountain. To find the invisible scaffold of the cosmos, we had to leave the sky behind and bury ourselves deep within the Earth. At the Gran Sasso National Laboratory, shielded by thousands of tons of rock that block out the noisy rain of cosmic rays, sits a vat of liquid xenon held at 100 degrees Celsius. This is the xenon experiment. It is a listening post designed not to look, but to hear the faintest whisper of the dark sector. For decades, the leading theory for dark matter has been the WIMP, the weakly interacting massive particle. The theory was elegant. It fit perfectly with supersymmetry, a framework that predicted a heavier invisible partner for every known particle. Calculations suggested that these WIMPs should have been produced in the Big Bang in just the right numbers to account for the missing mass. This coincidence was so precise it was christened the WIMP miracle. If WIMPs are the steel beams of the universe, they should be everywhere. As the Earth moves through the galactic halo, we should be plowing through a wind of these particles. While they do not interact with electromagnetism, meaning light, they should very rarely collide with an atomic nucleus. The detection mechanism is brutalist in its simplicity. We fill a tank with ultra-pure noble liquid, either xenon or argon, and wait. We are waiting for a single dark matter particle to strike a xenon nucleus head-on. This collision, called a nuclear recoil, would release a tiny flash of light, followed by a small burst of freed electrons. Imagine trying to hear a pin drop in the middle of a heavy metal concert. That is the challenge of detection. The concert is the radioactive background noise of the universe, traces of uranium in the rock krypton in the air, even the metal of the detector itself. We have spent billions of dollars and decades of engineering simply to turn down the volume of the background noise. We built the quietest rooms in existence. We purified the xenon to the atomic level. We waited for the signal that would confirm the WIMP miracle and reveal the architecture of reality. And we heard absolutely nothing. Silence in science is never empty. It is heavy with information. Every time an experiment like Xenon 1T Lux or Panday X concludes without finding a particle, it draws a line on a graph. This is the exclusion plot. The space above the line represents the properties dark matter cannot have. With every null result, we lower the line, shrinking the hiding place of the WIMP. We have now ruled out the most obvious versions of the WIMP. The miracle is fading. The particle is either interacting far more weakly than we hoped, or it is much lighter than supersymmetry predicted. We are now searching for a signal so faint that we are approaching a technological event horizon known as the neutrino floor. Neutrinos are extremely weakly interacting particles produced by nuclear fusion in the sun. For decades, they were the hardest things to detect. But as our dark matter detectors have become hypersensitive, the sun's neutrinos have transformed from a signal into a source of irreducible noise. We are approaching a level of sensitivity where the detector will start picking up solar neutrinos, indistinguishable from WIMPs. This is the fog that blinds our instruments. Once we hit the neutrino floor, traditional detection methods hit a hard wall. We will be trying to spot a candle flame against the glare of a searchlight. The null results of the last 20 years have forced a reckoning. The search box for the standard WIMP is closing. The silence suggests that dark matter might not be a heavy singular brick like a proton. It might be something else entirely, something lighter, wavier, and stranger. When your detector becomes too sensitive to tell signal from noise, you are forced to ask a different question. What if we are listening in the wrong place? What if the universe isn't built of heavy beams, but of a fine, vibrating mesh? If dark matter isn't a heavy WIMP, the next best suspect is the axion. The axion is a theoretical particle originally proposed to solve a flaw in the strong nuclear force known as the strong CP problem, but physicists quickly realized it had the perfect properties to be dark matter. Unlike the heavy, clumsy WIMP, axions would be incredibly light, billions of times lighter than an electron, and would behave more like a wave than a particle. Because they are so light, smashing them into xenon atoms won't work. They would just bounce off like a ping pong ball hitting a tank. To find an axion, we need a different mechanism. Theoretical physics predicts that inside a powerful magnetic field, an axion can spontaneously convert into a photon of light, specifically a radio wave. This is the Primakov effect. We try to induce this on Earth with experiments like ADMX using strong superconducting magnets, but our magnets are weak toys compared to the machinery of the cosmos. If we want to find the axion, we shouldn't look at our own machines. We should look at the high-energy factories that nature has already built. We look to the neutron star. Specifically, we look at magnetars, neutron stars with magnetic fields 1 trillion times stronger than Earth's. They are the most powerful magnets in the universe, generating magnetic fields between 10 billion and 100 billion Gauss, equivalent to roughly 1 million to 10 million Tesla. In the vicinity of a magnetar, even the vacuum of space itself becomes polarized. If axions are the dark matter, they should be streaming into these magnetars, caught by the intense magnetic field, and converted into radio waves. A magnetar shouldn't just be a dead magnetic core, it should be a glowing radio beacon screaming its presence across the galaxy as it converts a fraction of the surrounding dark matter into radiation through magnetic interactions. So astronomers pointed their radio telescopes at the nearest neutron stars, expecting to see this specific axion glow. They saw darkness. The neutron stars were radio dark at the predicted frequencies. Once again, the universe refused to answer. But just like the WIMP null results, this silence is data. It tells us that if axions exist, their interaction with electromagnetism is incredibly weak, weaker than our optimistic models hoped. We are left in a state of high-tension suspension. We have mapped the effects of the scaffold through gravity. We have seen it separated from the building in the bullet cluster. We have seen entire buildings missing their scaffold, as in the case of DF2. But every time we attempt to detect the material directly, it falls below the sensitivity of our instruments. The failure to catch the particle has led some to despair. But there is one final place to look, not in space, but in time before the structure was fully built. We can look back in time to the very foundation of the building before the lights were even turned on. If we cannot find the scaffold in the present, perhaps we must look for the moment it was first erected. Deep in the infrared images returned by the James Webb Space Telescope, astronomers have found three objects, JADES GS 0130, Z120, and Z110, that defy explanation. They date back to the cosmic dawn just a few 100 million years after the Big Bang. They look like galaxies, but they are too bright, too red, and too massive to have formed so quickly by standard laws, unless they aren't galaxies at all. Unless they are something else entirely, the primordial prototypes predicted by theory dark stars. In the primordial universe, the dark matter halo was much denser than it is today. As the first clouds of hydrogen gas collapsed into these halos, they didn't just heat up from pressure. They were heated by the annihilation of dark matter particles concentrated within the halo. This annihilation provided a heat source that stopped the star from condensing into a tight nuclear fusion reactor. Instead, the star remained puffy, cool, and colossal. A single dark star would be millions of times the mass of the Sun and large enough to swallow the orbit of Saturn. It would not shine with the harsh white light of fusion, but smolder with a deep infrared glow, like a giant peat fire burning in the dark. These primordial titans would be the missing link in our architectural history. When the dark matter heating can no longer counteract gravity, the structure becomes unstable and may collapse directly into a supermassive black hole, bypassing the usual stellar stages. This explains the inexplicable how the monster black holes at the centers of galaxies grew so big so fast. They didn't grow from scratch. They emerged from the collapse of structures governed by dark matter. We began this investigation with a sense of unease, the feeling that the visible world is moving too fast, held together by nothing. We end it not with a capture, but with a map. We have traced the centrifugal tear in the spiral arms of Andromeda. We have witnessed the chassis separation in the wreckage of the bullet cluster. We have stood in the deafening silence of the xenon bunkers and stared into the infrared dawn of the first structures. We still do not know the name of the particle, but we know the shape of the house. For most of human history, we stared at the lights in the sky and thought they were the universe. Now we know that the stars are merely a luminous veneer clinging to the unseen stonework of a vast cathedral. The structure is vast, ancient, and indifferent to us, but it is there, and it is holding us up.